There are 5 basic operations that we're going to want to be able to do with vectors. Adding vectors, subtracting vectors, multiplying a vector by a scalar, these 3 we've already looked at. The next 2 are going to be ways that we can multiply 2 vectors together. And the first of these is a way to multiply 2 vectors together that's going to give us back a scalar. So our new operation then, this dot product, is going to allow us to take 2 vectors, multiply them together, and we'll end up with a scalar, and we want to understand the information that that scalar is telling us. So for starters, let's think about our rules for how we do this. So let's look at an algebraic rule first. So what we'll see is there's a way that we can do this algebraically, there's a way that we can do this geometrically. We want to understand both of those and understand the information, how to do them, and the information that they're trying to tell us. So let's say I've got 2 vectors, vectors A and vector B. So vector A is axi hat plus ayj hat plus azk hat. So I've written it out in Cartesian form. Vector B, bxi hat plus byj hat plus bzk hat, again written out in Cartesian form. And so A dot B, and the first thing we want to notice is that little dot is telling us what our operation here. So instead of a plus sign or a minus sign, that dot is telling us we're taking the dot product between vector A and vector B. And what it says is we're going to multiply the 2 x components together, plus multiply the 2 y components together, plus multiply the 2 z components together. So our algebraic rule for calculating out the dot product between 2 vectors is that it is basically the sum of the products of the corresponding components of each vector. So if you know your vector's components, all you're going to do is take x components, multiply them together, plus y components, multiply them together, plus the product of the z components. That's the algebraic rule. The geometric rule says that we get the dot product, we get that same answer if we take the magnitude of vector A times the magnitude of vector B times the cosine of phi, where phi is very specifically defined to be the angle between those 2 vectors. So notice I've got A that's pointing off to the right, B is pointing up and to the right. There's some angle phi between those 2 vectors. So I can calculate out the dot product as magnitude of A, magnitude of B times the cosine of that angle. Now there's a couple of other ways that we can think about this. So notice if I take that cosine phi and partner it up with the B, what that means then is that I'm thinking about breaking B up into 2 components, one that is parallel to my vector A, one that is perpendicular to the vector A. And so B cosine phi is that parallel component. So I can think about the dot product is A times the component of B that is parallel to A. Or I can also think about the same thing where I line things up along vector B. So again, I can take vector A and use that angle phi to break vector A up into 2 components, a component that is parallel to B and a component that is perpendicular to B. And again, my dot product says I want to multiply vector B times the component of vector A that's parallel to B. So what this means is that the dot product is giving us information about how much our 2 vectors lie along the same line and point in the same direction. The more our 2 vectors line up, the larger the dot product becomes. How is it that the dot product is giving us information about the relative direction of our 2 vectors? Well, the magnitude of vector A is always a positive quantity. The magnitude of vector B is always a positive quantity. But of course, A dot B can be positive, it can be negative, it can be 0. And so whether it's positive, negative, or 0 has to depend on this cosine term. And so there are basically 3 general rules. One is if that angle phi is less than 90 degrees, then you're going to have cosine of an angle less than 90 degrees. That's always positive, which means your dot product will be positive. So positive magnitude times positive value of the cosine function, your dot product's positive. On the other hand, if your vectors are perpendicular to each other, well, in that case, phi is 90 degrees cosine of 90 degrees is 0. So when your vectors are perpendicular to each other, that's the situation where their dot product is 0. So knowing that the dot product between two vectors is 0 is another way of saying that you know those two vectors are perpendicular. The third case is, well, what happens when phi goes past 90 degrees? Here, basically I have phi that's somewhere past 90 degrees. Cosine of an angle between 90 degrees and 180 is always negatively valued. So this is the situation where now I have cosine values are going to be negative, which means my dot product is going to be negative. If your dot product is positive, that means that in general your vectors point in the same direction, right? There is some component of one vector that points in the same direction as the other. If your dot product is 0, your two vectors are perpendicular. If your dot product is negative, that means the component of one vector points in the opposite direction as the other. So if you think about this case on the left, the component of B that is parallel to A points back to the left, A points to the right. So in general, the component of B that lies along the same line as A points in the opposite direction as A. And so that's what we're talking about when we're talking about the relative orientation. Are they more pointing in the same direction? Are they perpendicular to each other? Are they more pointing in opposite directions? Of course, there's some special cases of that. So if A and B do point in the same direction, then the angle between them is going to be 0 degrees. Cosine of 0 is 1. And so the dot product is just magnitude of vector A times magnitude of vector B. Again, we've talked about if they're perpendicular, the dot product is 0. Right? The angle between them is 90 degrees. Cosine 90 degrees is 0. Therefore, the dot product is 0. The other interesting one, of course, is if they point in opposite directions. So now the angle between them is 180 degrees. Cosine of 180 degrees is negative 1. So notice I'm going to have magnitude of vector A times magnitude of vector E times negative 1. So here's a situation where I get negative AB. So you can see that sort of these two, top and bottom, they're the extremes. Right? This is the largest positive value you can get for your dot product. Magnitude of vector A times magnitude of vector B. This is the largest magnitude that is negative that you can get. Again, it's just the magnitude of the two vectors multiplied together, but now it's negative, telling you that those two vectors lie along the same line but point in opposite directions, rather than lying along the same line and pointing in the same direction. And so as you go from basically this situation up top and start to rotate one of your vectors relative to the other, you're going to have a positive dot product that gets smaller and smaller and smaller until it finally gets to 0 when your two vectors are perpendicular. Then as you keep rotating one of your vectors relative to the other, now you're going to have negative dot products, and that value is going to be negative but increase in its magnitude until you get to the point where they lie along the same line again, but now point in opposite directions. So your dot product is constrained to lie between positive AB and negative AB, and the relative orientation of your two vectors is going to be able to tell you the sign, should it be positive or should it be negative, and then how large should that dot product be.